Thanks so much for joining. This is Border City Data at Hackforge. My name is Doug Sartori. I am a principal consultant at Parallel 42 Systems, and I help organize Border City Data. Today, we're going to be talking about SQL. This is the second in our series on SQL basics. So today we're going to focus on relationships between data and how you can effectively query data in a relational database. There will be time for questions afterwards. I'm trying not to assume too much knowledge. If you attended our first session, then you'll have a pretty good grounding and you'll be pretty ready to go for this one. If you didn't, what we covered was the select statement, how to select data and grab data from a relational database. So you'll see a lot of that tonight. You'll see me write some select statements. And as we do that, I'll quickly go over the parts of the SQL statement just so that you can catch up. So I thought a good place to start with this discussion would be just talking about relational databases themselves. So relational databases are, in terms of our industry, which is still a pretty young industry, relational databases are a relatively old technology. Back in 1970, the relational database was proposed as a way to solve a number of problems that people were finding that they were having with the data stores of the day. And primarily, those problems revolve around data anomalies, meaning essentially that you have two versions of the truth because you have data that contradicts itself. Other anomalies that you can get when you are storing data not in a relational way include delete anomalies when you remove a record and that is the last record associated with some other piece of data, and then you lose data that you actually wanted to keep. Relational databases are a structure that will be pretty familiar to you, I hope. Essentially, if you think of the tables in a relational database as spreadsheets, you're not very far away from having an understanding of what a table is. Tables are, they are columns and rows, each intersection of which contains a unique point of data. So far, it sounds a lot like a spreadsheet. The difference between a spreadsheet and a relational database table is that relational database table columns are predefined. They are defined in terms of their name, and they are defined in terms of the type of data that they store. So unlike a spreadsheet, in a relational database table, you are going to find that you can only store data of a specific type, be that a number or a string of characters or a date or some other more complex type. You can only store that kind of data in that particular column. That is another feature of relational databases that is designed to eliminate errors. In this case, the basic error of having the wrong kind of data in a particular column. The rows in a relational database table represent the individual records. So in that respect, it's an awful lot like what you may be familiar with in terms of a spreadsheet. Relational database tables each store only information about one kind of thing. There are a whole set of complex rules about how to structure a relational database. That's called normalization, but it all boils down essentially to tables are independent entities that only store information about the entity that they are representing, and you make more complex sets of data by joining tables together, which is what we're going to be talking about today. And you do that by relating tables to each other using keys. Okay, that was a big info dump. So let's dive in and get into a little bit of detail. Before we do that, let me tell you some of the pros and cons of relational data. So the pros are that relational databases save space. They save space because you do not repeat data. So if you had a spreadsheet that represented an address book, for example, and you had a column in that spreadsheet that represented the city in which people live, you might find that the same city is repeated many, many times. In a relational database, you would not have that repeating data. Therefore, your storage would be smaller. And you don't run the risk of, as I mentioned before, of having anomalous data where, for example, in one row, you have an abbreviation for a province or a city, and in another row, you have a different spelling or the complete name. By using keys, which are typically, most frequently, keys in a relational database are represented as integer numbers, meaning whole numbers, 1, 2, 3, 4. Using those numbers as keys saves space, reduces storage space. Relational databases are also designed for very quick inserts. So data can be inserted more quickly in a relational database than in other types of data stores. The corresponding con to that is that sometimes reads from a relational database are a little bit slower. And so we see that with reporting or aggregating data over longer periods of time, that relational databases sometimes don't perform as well. That's why we see other technologies like data warehouses that are designed for solving that type of problem. And the relational database structure, as I mentioned, eliminates certain classes of error. If you have a properly structured relational database, you're just not going to see some of the common data problems that you see with other types of data stores. Besides being a little bit slower reading data, some of the drawbacks of relational data is that it's not as intuitive, and we're going to see that. It's not as easy to understand as a simple table that shows you all of the data in one kind of glance that you're interested in. When you're working with relational databases, you are going to have to connect those tables together to be able to get anything meaningful out of it. And that can result in some fairly cumbersome queries. And that's what we're going to be talking about today. So let's dive in. This little diagram here shows two tables. These tables would be in a database that represents some kind of education management system. And we have teachers and the classes that they teach. So as we talked about earlier, each of these tables represents one kind of thing. There is a table of teachers and a table of the classes that they teach. No data from classes is stored in the teachers table, and no data about teachers is stored in the classes table. Instead, what you see in this case is a relationship is defined between the two tables to help us understand how we are going to use that data and how we're going to have to join those tables to query them. And it also helps the database itself understand the relationships between data. So in the classes table, we have a teacher ID, and that is connected to the teacher ID in the teachers table. You'll see some small symbols that are next to the teacher ID in each table. Essentially, what this is doing in visual form is modeling the relationship. So one teacher represents or lines up with 0 to many representations of that teacher in the classes table. So we cannot have more than one teacher ID that is the same in the teachers table. That is the primary key for that table. It must be unique for each record. So we know that a teacher ID, no matter where it is in our database, references one and only one teacher. But in the classes table, we can have many instances of the teacher ID because one teacher could teach many classes, or they might have the semester off and teach 0 classes. So there is no requirement that a particular teacher ID will be present in the classes table. We call that a foreign key. So it is a foreign key in the classes table that is pointing to the primary key in the teachers table. The classes table also has a primary key, the class ID. So that is the unique identifier in that table, and it represents one and only one class that's being taught at this particular school. So using this kind of structure, we can store our data in according to the principles of database normalization. We can make sure that we have only one instance of each entity that we're interested in, and therefore we are not going to have the type of data anomaly where we have multiple versions of the same thing, multiple versions of the truth. Okay. So now that we know about tables, let's talk a little bit more about the kinds of relationships. So I showed you one relationship on that previous slide, and that was the one-to-many relationship. On this diagram, that is in the middle, and we can see that that is the product line. The product line table in that diagram connects to the product table, and you can imagine if you could see the full relationship diagram, there's probably a product ID that is referenced in the product line table. There are other kinds of relationships, though. That top one is showing us a one-to-one relationship. You don't see this type of relationship very often. One record in one table relates to one and only one record in another table. It's a fairly rare type of relationship, but you should be aware of it because you will see it from time to time. And then the bottom one is the most complex type of relationship, and that is a many-to-many relationship. So in this case, both the product table and the customer order table can have many records at the same time. So how does that work? Well, we don't actually want to represent that data repeated in either table. So we create an intermediate table. In this case, order line would be the name of that table. And order line will connect those two tables together. And every entry in the order line table will have one foreign key representing the primary key from each of those two tables. And that's used to model complex relationships. And it is a real lifesaver in terms of database design. So you need to be aware of the three different types of relationship that you may encounter in a relational database, because each of them will require a slightly different strategy when it comes time to create a query, write a query using SQL to actually connect that data together. So we're going to walk through some examples tonight, and to do that, we're using the Adventureworks Database. This is a product that is put out by Microsoft. Adventureworks is a sample database for Microsoft SQL Server. I chose it as our sample database for a couple reasons. It is free to download. Just as Microsoft SQL Server is free, you can download SQL Server Express for Windows or Linux and run it on your own computer without paying any money. And you can also get a free copy of the Adventureworks database. So it's a great way to learn about SQL, and it's a great way to learn about Microsoft SQL Server. There's lots of resources available online for this database. It has been around for many years. We're using the 2008 version of the Adventureworks database tonight, but there are many newer versions for newer versions of Microsoft SQL Server. This is the one that I use in testing when I evaluate potential database programmers, either for myself or for a client. I usually run them through a test that uses the Adventureworks database. And in fact, tonight you're going to get to see a couple of the test questions that I sometimes use. So that's a little bit of a tip for you if you're planning on applying for a job in this particular city anytime soon relating to data. You just might see some of these questions. And it's commonly used for skill testing in just the kind of way that I was describing. So that is the database that we'll be using. And here is a tiny piece of the schema. So this is a diagram that is showing you the relationships between a subset of the tables in Adventureworks. Adventureworks has dozens of tables. It represents a very complex database for a retail operation. There's lots and lots of stuff in there. So we're just focusing on a few tables to minimize the confusion and to, excuse me, and to make sure that we're focused in on just the things that we want to see. But if you go to your web browser and Google Adventureworks database diagrams, you'll find many different visualizations of the entire database. But this is a nice one because it's nice and small. So what I want you to look at here is the way that in a practical database, even though this is a sample, it's built very much the way databases that are used in industry would be. It is a good example of the kinds of relationships that we will see. So tonight we'll be looking at products and sales orders and customers. So let's look at the relationships between those tables. The product table, you can see the primary key there with the abbreviation PK. That represents the product ID. That is the record, the single record that represents one specific product. And the product table has a couple of foreign keys. It has a foreign key to a table of categories. And those categories actually are really interesting in themselves. If you look over at the product category table, it has a primary key, the product category ID, but it also has a foreign key. And what is interesting about this is that it actually points to itself. This table has a foreign key, parent product category ID, that's pointing to the product category table. Why is that and how does it work? Well, when you use this type of a structure, what you're doing is you are creating a hierarchy. So we are allowing for a product category to have a parent product category, and for that product category that's the parent to have its own parent. So by using this structure within a single table, we can model a complex hierarchy of product categories. So I'm going to just go over that again real briefly. If you take a peek at that table, product category, you'll see that there are 3 columns: the product category ID, which represents the primary key; the parent product category ID, which is a foreign key, which means that it is pointing at a different record in the same table. So if you can imagine, you have item 1, product category ID 1, and its parent is product category ID 2. That would mean that the product category 1 needs to look at the record in the same table represented by the primary key product category ID 2 in order to know which record is its parent in that hierarchy. So that is an interesting little way of structuring data. And that's kind of something that's relatively unique here. The other one I wanted to point out to you is the relationship between the sales order header table, which has a primary key of the sales order ID, because that represents the header information, the sort of the top line information on a particular sales order. And it has 3 foreign keys, but those 3 foreign keys only point to 2 tables. There is a customer ID foreign key that points to the primary key of the customer table. So that's how you identify which specific customer is making a purchase on that sales order. And then it has 2 foreign keys to the address table. And one of those represents the bill to address, and the other represents the ship to address. So you see that's modeled in the diagram with two separate lines connecting the sales order header with the address table. And each of those foreign keys could point to a different record in the address table, but all of the addresses, whether it's a ship to address or a bill to address or some other type of address, is all stored in the same place. Again, relational databases, we want to store one kind of thing in a table, and ideally we also want to have only one table that represents that kind of thing. So sometimes you'll end up with interesting relationships like that. Our sales order header table has a relationship to the sales order detail table. A sales order detail represents one single line in a sales order. So if you think about a receipt or an invoice, that header information, and you can see the columns that represent the header, the order date, who is the customer, where are we sending the bill, where are we shipping the product, how are we shipping it, what's the total amount of this order, et cetera, et cetera. That's all of the information that applies to the entire order. But there are also each individual line in that order. You may have ordered a bicycle, as well as a helmet for your bicycle, as well as a pump or a spare tire. And each of those would represent a separate line on the sales order. And that is modeled here in the sales order detail table. So the sales order detail table has a foreign key to the sales order table, or sales order header table, excuse me, and a primary key that represents that one individual line. Okay, I'm going to stop there. We could explore this whole section of the database together, but hopefully you get the idea. Relationships between tables can be complex. They can surface in different ways depending on how your data is structured and how you want it to be modeled. And you need a tool like this. You need a diagram to be able to easily understand how tables relate to each other and how you should write your queries. So this is an essential part of documenting a database in a relational database, because it can be very difficult to understand the structure of a database just by looking at a list of tables and columns. Okay. So hopefully you folks have a pretty good understanding of what this database looks like and how it works. So now let's dig into the different ways in an SQL query that we can join data. So we use the join clause in an SQL query to get data from multiple tables, and we'll get to a practical example in just a moment. The join is specifying how exactly SQL should decide which rows to show you in the result set. There's three main types of join and a few different variations. There is a classic diagram showing the different types of SQL join, and I'm sharing it here on my screen. In the center, we see the most common type of SQL join, the inner join. And what we're looking for when we ask the database engine to do an inner join between two tables is to give us only the records back that have a match in both tables. Okay, so going back to our diagram here, we would use an inner join on, for example, when connecting the sales order detail table to the product table, because if we are getting back a list of the products that were purchased on a particular sales order, we only want to see the products that actually were purchased. They only want to see the products that are represented on sales order detail. And conversely, if we have a line in our sales order that doesn't have a matching product, we probably don't want to see that either. In this case, that would be a problem with our data, but just by way of example, I wanted to share with you that concept, and that is what we would use an inner join for, matching rows in both tables. Okay. Then we have a couple of different kinds of left and right join, and we'll get into the details on that. But essentially, the question that you have to ask yourself when you're doing the left or right join is whether you want to see the intersection rows as well as the rows that don't have a match in the left or right table, or if you want, well, those are your two options essentially. And finally, there is the full join, which is pretty rarely used. So here's a little bit more detail on those types of join. The inner join, as I said, is the most commonly used way that we join tables together. And it gets only rows from both tables that match the condition. Okay, so we're going to do an exercise now. I will switch over to my database window. And our exercise here is to get the top 10 customers in terms of sales by customer ID. Okay, so what we want to do first is understand where in the database we're getting that data. Where are we looking for this information? Okay, so we need to identify the customer, and we need to know how much they purchased. Sales orders have a total amount, right? There's a total amount column in the sales order table, the sales order header table. And let's take a look in SQL Server here. Sales order header. I'm just going to expand that and look at the columns. Okay, so we have the customer ID. We're interested in that because we want to know who the customer is. And we have the subtotal of the order. Okay. And we have the total due, which would be the amount with tax. So let's just use the subtotal this time. Okay. And let's take a look at what that looks like. So we would want to know the customer ID and the subtotal from, whoops. It's a bad habit that many more elderly SQL developers like myself will have. Back in the days before we had syntax highlighting in our editors, we used to type keywords in SQL in all caps as a way to distinguish column names and other information from the keywords. Now that we have syntax highlighting, I think that's kind of an anti-pattern. It's not really a way that you should do things, but unfortunately, old habits die hard, and I still do it from time to time. Okay, so sales order header is our table. All right, we can execute that. And I forgot to prefix it with my schema. Okay, there we go. So what we have done here is we have asked the database engine to give us specifically these two columns. Okay, so we use the select statement to tell the database engine that we want to see a result set. We want to get a result set back. And we are specifying the columns that we want to see. And we do that by supplying the column names in a comma separated list. Once we've specified all of our columns, we use a from clause and then the database table name that we want to query in order to get the data that we want. So a select clause with the with the columns specified, and a from clause with the table name. This is about as basic as a query gets. One thing that you might be interested to know is that you can use an asterisk to get all of the columns in a table. It's a shortcut that allows you to get all the columns in a table in one simple query. Select star from. It's something that you very often use when you are just exploring the data in a table, trying to figure out a new database that you're working with. Okay, So right now what we've got is a list of customer IDs and the subtotal on each order. So there's a couple things that we probably want to do here. We probably don't want to use a customer ID to tell us who we're dealing with. It's not very easy to interpret. That is an internal database representation. So in order to get more information about the customer, we're going to want to join that table, the sales order header table, to the customer table in order to get customer information. So we will specify our join type. This is an inner join. That's usually what we want. It's where I typically start when I'm writing a query and then figure out if I need to do something different. And that is the sales customer table. When we join two tables, we have to tell the engine, we have to tell the SQL database engine how we want those tables to be joined. You might have multiple options. The foreign keys and primary keys might not be specified in the database, or you might want to use a non-key value to join two tables. So you have to tell the database exactly what you want. And we do that by telling it to join that table on a specific expression. And what we're going to supply here is a Boolean expression, okay? Supplying a column from each table and an equivalency operator. And that Boolean expression returns either a 1 or a 0. It is either true or false. And what we are asking it for is all the rows where this specified relationship is true. One thing that I want to do right now is supply some aliases. So this is just a nice little piece of syntax in SQL. You don't have to type out that full table name when you join tables. You can use the abbreviations that you specify in order to connect them and also to identify the columns. Because sometimes two tables will have columns which have the same name. And you can't have that level of ambiguity. You have to tell the database exactly what you want. Microsoft SQL Server is smart enough that if the column name is unique across the two tables, you don't need to specify which table it's coming from, but it's a good practice to do that. So we'll use the customer ID and the sales from the customer table and the sales order header from, or the subtotal from the sales order header table, sorry. And we now need to specify that join. Okay, so this would be sales order header customer ID equals C customer ID. So let's walk back through that. So we are selecting rows from sales order header. We are joining to that table, to sales order header, we are joining the customer table, and the column that we're using is customer ID in both tables. Remember that customer ID is a primary key in the customers table and a foreign key in the sales order header table. Okay, that didn't change our result set any because the customer ID is the same in both places. So we could choose to show the account number, and that might be what we want to do. And now we have the account number coming from the customer table as specified by the customer ID in the sales order header table and the subtotal from the sales order header table. Okay, I hope you're with me so far. This is still not real easy to read. And I notice when I look at the customer table that there is a person ID. So there is a person record that's associated with each customer. So let's take a look at the person table. Okay, here we go. Person. And we can join that table as well. Inner join person P. And now in this case, now it's getting complicated. We're joining three tables together. In this case, we are joining the customer table, which has a foreign key for the person ID that points to the primary key of the person table. So that's the relationship that we want the database to use when it's returning results. So person ID equals, whoop, and what is the, okay, let's try that. All right, great. It seems to still be working, but now we can actually get the name from the person table. So we can specify the person's first name and the person's last name and the account number. And now in our result set, we can see the actual name that is human readable of the person, their account number from the customer table, and their subtotal from the sales order header table. We're still not done because what we don't know here is we don't know what actual order that subtotal relates to, but that's okay, because what we actually want to see is the we want to see the total that each person has purchased from us. We want to see the total amount that each person has spent with us. So what we want to do now is we're going to use a function, a database function that will give us the total of the order subtotals. So what we're looking for is all of the subtotals for all of the orders related to a specific person, summed together. Let's try to execute this. Uh-oh, we get an error, and we get an error back. Well, the SQL engine is kind enough to give us a pretty detailed explanation. And what it's telling us is that every column in this select clause has to either have an aggregate function or it needs to be grouped. So we're going to learn about something new right now, and that is the group by clause, because we actually want to group our data. So what SQL is telling us here is that we have inadequately specified the data that we want. Okay. So in this case, basically, everything that we are not using some kind of an aggregate function, like there are many other aggregate functions that we can use. We can use max to get the highest value, or min to get the smallest value, et cetera, et cetera. Any column that does not have an aggregate function is going to need to be a part of our group by clause. So we have to specify all of these columns. And actually, the way to do this, now you may ask, why am I doing it in this order? And there is a good reason that I'm going to tell you in just 1 second. Sometimes you have elements that you want to display in your result set that don't actually need to be part of your grouping clause. But you also don't necessarily want to perform any kind of aggregate function on them. So in this case, in our query here, it's the last name and first name are really kind of the orphans in this list. We want to group this result by individual customers, and we want to get the sum of the subtotals for each sales order. But we have a problem because we're specifying tape or columns in our result set that we don't actually want to aggregate. So there are 2 ways that you can deal with that. One way is what I've done here, which is specified the grouping by account number first, with the knowledge that the first name and last name will not have any unique rows within that set of account number, because they're dependent on it, right? We're joining person on the customer ID, which is a proxy for the account number, and the person table is not going to have any rows that do not match up with that account number. So we can specify it like this, which is going to give us the same result as though we didn't have the person table joined here at all. The other way that you could do it, and I'll just comment out this section and show you. The other way that you could do it is supply an aggregate function in your select list, oops, to get the, to some harmless aggregate function that you know is not going to have any impact on your output. And the reason, again, that you know it's not going to have any impact on your output is that each of those records are dependent on the actual value that you're aggregating by. I think it's cleaner and nicer to use the group by clause and specify all the columns there. I just don't think it's very nice to apply a function on a column that you are not actually intending to get any value out of. To me, this is a little bit easier to understand. I've seen different people do it different ways. One last thing that we have to do is because we are using a function on this subtotal, SQL doesn't know what column name we want anymore. So I am specifying that I want to show this column as subtotal in our result set. Let's see what happens. Okay, so now we've got the aggregate of our orders for each customer, each person aggregated, and there is only one row per account here, which means there's only one row per person as well. This is great, but what I'd like to do now is I'd like to get my results in a certain order, because I actually want to see who my best customers are. I don't want to just get a random list of customers back and their aggregate order total. I want to see who my best customer is. So to do that, we are going to use an order by clause. And this is another tool that we can use in SQL, and this will allow us to specify the order that we get results back in. If you don't specify an order by clause to tell the server what you want, what order you want results back in, it is going to just give you what's called the natural order, whatever is convenient for SQL, whatever is convenient for the database engine, that's how it's going to give you your results. So instead, we want this ordered by the sum of the subtotal. Okay, we have to specify that function again, because the order by clause doesn't know anything about what we've done up in the select list. So we're going to order it by the subtotal, and then we're going to specify that we want it in descending order. SQL assumes that you want results in ascending order unless you specify otherwise. So now when we run our query, now we know who our top customers are. Before we leave this one, I'm just going to do one more little thing. I'm going to show you how we limit our result set. So if we only want to see the top 10 customers, we can add to our select statement, we can add the specification top and a number to tell it that we only want a specific set of rows back. And there you go. There are the top 10 customers of our store according to how much money they've spent with us. Okay. All right, cool. Now moving on. Let us go back to our slides for a moment. That was the inner join and a whole lot of SQL stuff. I hope that I'm not going too fast, and I hope that that was easy enough to understand. And now we're going to talk about left and right joins. So these are specified differently, but they essentially do the same thing. This is a situation where you are getting all of the records from one of the two tables that you're joining, and only the matching records from the join table. So you would do this in a case where you want to know everything about one table. You want all the information from one table, but only even if there is no matching data in the table that you're joining to. So the example that I've given here is we might want to list all of our products and find out how much has been ordered from of that particular product. But we might have a new product that has never ever been ordered, in which case an inner join would not return that row to us. We would not get any information back about that row of data, about that particular product, because the inner join would eliminate any results that don't match on both sides. So we would want to use a left join in this case. Or if the table that you're interested in that has the data that you want to see the full set of is on the other side of your expression, then you want to do a right join. That's pretty, that's less common than a left join, just based on the way that folks typically type right queries, but you can do it either way. And it's useful when the table that you're relating to has sparse data, meaning that not every piece of data that could exist does exist. Another good example is to go back to our initial set of example tables. You might have a teacher who is teaching no classes. In order to find those teachers and make sure that they were represented in your result set, you would want to use a left join from the teachers table to the classes table to make sure that if there were no classes being taught by a particular teacher, you still could still get your information. Okay, so let's take a look at the database again and get our list of products and the sum of quantity ordered. Okay, so we're going to clear all this out. Okay, so let's just start with our simple query. Let's just take a look at product. Oh, I got it wrong. I think I've got person on my mind. Product is production. Okay. Okay, so here is our full product table. Okay. The product table is right here, and it has a primary key, the product ID. So let's grab the product ID and the product name. Okay, and just in case there are duplicates, let's grab the product number. Just in case there are duplicate names, that's something that could happen. You might have two products that have a very similar or the same name, but have a different product number, because that's actually what's unique. Okay, so there's our list of products. Now, what we want to do is we want to find which products have been ordered and how much has been ordered. So to do that, we want to, I'll just add a little alias for our product table. We want to use sales order header. So we are going to left join sales order detail is the table that we want. Let's expand that guy so you can take a look at it. Okay, here we go. And there's the product key as a foreign key on the sales order detail, SOD on. Okay, and in this case, it is P product ID equals SOD product ID. Okay. And now that we've done that, we can add our aliases in our select list. We can sum the order quantity from sales order detail, total ordered. Okay, and remember that we need to group now. And the same situation applies where we are selecting multiple rows from the same table. they are all going to be dependent on that product ID. So we can use the product ID first in our group by clause and then safely specify the other columns in any particular order that we want, knowing that it is not going to mess up our grouping. Okay, so let's take a look at that. Okay, now we see, okay, this is great. So what we're seeing here, when you see a null in the result set, that yellow background, capital, all caps null, that is not data. And this is a really important point that I want to stress. That is not data. That is a null marker. That is identifying to you the absence of data. Okay. It's really, really important to understand the difference between a null marker and data. We only want to see data. When we see a null marker, that means there's nothing there. In this case, that's what we wanted to see, because we want to see products that haven't got any orders against them. But generally speaking, when you're seeing null results in your data, you want to make sure that it's something that you want to see. Okay, so let's just see what it would look like if we did an inner join. Okay, so there's a whole lot less rows, and we don't see any null markers. So we're not seeing our complete product list anymore because we're doing an inner join, because we're only getting the rows that match on both sides of our expression. Okay, we change that over to a left join, and you see here our result set was 266 rows with an inner join. And now we have 504 rows. So we have a couple hundred products that have never been ordered. If we used an inner join to generate our product list, we would not have seen any of that data. So that is pretty important to see. So one more thing I'll show you, since we have a couple of minutes here. One of the things that you can do is you can actually you can specify to the database what you want to do when there is no data. So you may have a representation in mind rather than a null marker that you want to see in your output. And this is particularly useful when you're writing a query that is going to generate a report or that is going to feed some kind of representation directly, and users are going to see that result. So we have some options here. And in this case, we know that a null marker means that 0 have been ordered. So we can actually improve the quality of our output by specifying to the database what to do in the case that there is null data or no data there. And that is to replace the null marker with something that's going to be meaningful to our users. So in this case, we know that null means 0. It doesn't always mean 0, but in this case, it means that 0 products have been ordered. So we can add the coalesce function, okay? And coalesce is a cool little function that basically allows you to specify what the database should give you if there is no data in that column for that particular row. In this case, we are wrapping it around our sum function. So we are telling the database engine that if there is no total because there's no matching row in the right-hand table, show a 0. Okay, that might be what you want to see. Sometimes you might want to use another piece of data. So an example there might be if you have a nickname column, a preferred name column that is only sometimes populated. My full name is Douglas, but people usually call me Doug. I might have Doug in my preferred name column and Douglas in my first name column. Okay. Someone else, Lauren, who's on the call, Lauren might not have a shortened version of her name. So there would be nothing in that nickname column. That would be a good use of coalesce, where we're actually specifying 2 columns. In this case, we know that there is a consistent value that we want to see when there is no data returned for a particular row, that's a 0. We specify that in our coalesce function, and we're off to the races. So that is a left join. Okay, let's go back to our slides. There's one more case that I wanted to show you. Okay, this one is kind of a crazy one, the full or cross join. What this does is the full join does a complete matching every permutation in the two tables. So every row in the left table and every single row in the right table, which is also called a Cartesian product. This is very rarely used. Typically, you only see this used when you are trying to populate some sample data, or you are doing some very unique specific tasks. So in this case, I have a query that is going to populate all combinations of hour and minute. Okay, so what I've done, and I'll show you what I've done right now. There's some stuff that is kind of beyond the scope of what we're talking about today in this query, so don't mind that stuff. It's just for the purpose of creating this output. So what I've done is I've created two temporary tables in the database, one called hours and one called minutes. And then I use a little procedural script here to populate the hours and minutes tables with the numbers 1 to 12 and the numbers 0 to 59. So hours 1 to 12, minutes 0 to 59. So now that that's done, I'll just comment that whole section out so we don't have to worry about it anymore. And let's take a look at our tables. Okay, that hash sign in front of the table name is a just as a indicator that this is a temporary table. I didn't want to actually create a database table for this. So I just created a temporary table in memory. Okay, what do our hours look like? Okay, there they are. Hours 1 through 12. Let's take a look at our minutes. Okay, minutes 0 through 59. Okay, so we've got two tables. One contains all of the possible hours on a 12-hour clock, and the other one contains all the possible minutes. So just for fun, I wrote this little query which uses the cross join, and what it does is it cross joins those two tables. Okay, and I'm ordering it by hour and minute so that it's easier to see what it's doing. Let me just bring this up a bit so that you can see more of the output. Okay, remember there are 12 rows in the hours table and 60 rows in the minutes table. But when we do a cross join, we get 720 rows back. And you can see that every possible permutation is represented in our result set. So we have, I guess, yep, we have every hour from 1 o'clock. I didn't get too fancy with my output, so we don't have leading zeros on our times. You'll just have to forgive me for that. But we have every possible minute on that 12-hour clock is represented, and we populated that real quick because we used a cross join. Again, not a particularly useful type of join in practice. It's not something that you will find yourself using very often, but it's good to know that it's there. And in some niche cases, there might be a use for it, like populating a representation of the minutes in a day. Okay, so finally, I just want to leave you with a couple of thoughts about what you should be thinking about when you are writing queries in order to do it effectively. Number one, most important thing is know your data, understand the structure of the data, understand the relationships between the tables. Look at the database diagram. If a database diagram doesn't exist, make one. I can't stress this enough. You do not want to get unreliable or erroneous results because you didn't understand the data that you were querying. Before you execute your query for the first time, you should think about what that result set should look like. What am I expecting to see? And test those expectations. I think it's a really good idea to get in the habit of writing test queries and queries that QA your code and validate that what you're doing makes sense. A lot of times with simpler queries, you can do that just by introspection and thinking about it, but it also helps to actually do some testing to understand the result sets that you're looking for and make sure that the results you get back make sense. And that goes to our third point. You want to test and evaluate that result set. This is something that I probably spend as much time in my day-to-day work testing and evaluating my queries as I do actually writing them. It's an essential part of the work. It is not something that you can skip. Okay, so that is everything that I had to tell you today about querying SQL. So we're at an hour, but if anybody wants to stick around for a couple minutes, if anybody's got questions, please go ahead with your questions. And I see Sharad, you've got your hand up. So go ahead and unmute and fire away.
Hey, Doug. So the question I had was like, can the full join be accompanied by a conditional statement? Like if I want to do a Cartesian product where the product looks like that, where the product looks like a certain thing that I have in mind.
Yes.
That bit? Okay.
Yes, and I'm so glad that you mentioned that. The inner join and left join are actually fairly recent innovations in SQL syntax. Once upon a time, everything was done by just what you say, using a full Cartesian join, and then in your where clause, in the where clause where you specify what rows you want to see, that is where you would specify the specific conditions for those joins. You can still do it that way. In fact, some people do. Some people who whose experience with databases goes back a little earlier than mine, you'll still see some queries written that way. I think it's better to use the join syntax though. And the reason being that it makes it a lot easier for someone who's reading your code to understand what parts of your query are there to connect tables and what parts of your query are there to narrow the result set. They're doing the same thing, but there is a sort of, there's a difference between the two in intent. And I think it is better to separate them, but yeah, absolutely, you can do that. Okay, anybody else have any questions for me? Going once. Okay, that then concludes our talk. Thank you everyone for joining me tonight. I hope you got something valuable out of it. I really enjoyed preparing for it, and I had a lot of fun talking to you about it. So hopefully you're going to take this knowledge and use it in your day-to-day life, and hopefully it makes you a happier and more productive individual. Thanks for watching, folks. Take care.